This decision support part is basically split up into three parts. The first I'll talk about when you have explicit constraints on your planning process, and I'll elucidate the nature of those constraints in the next part of the presentation. There's also a part of implicit constraints, dealing with the unspecified preferences of humans. Your planner needs to deal with that sometimes. So Rao will deal with that, and then we'll also talk a little bit about incomplete dynamics. So what happens when you don't fully know what are the actions in the world and so on. Okay. So the first part where you talk about explicit constraints, I will actually demonstrate this in the context of this continual planning and replanning problem. Okay. So this is essentially a problem where in any human-in-the-loop planning scenario, right, you have new information that's coming in all the time. Okay. This information could either come from the sensors on your agent, right? So if you're thinking about a human-robot teaming scenario, your agent could basically be equipped with a bunch of sensors that are sending you new information, which force you to replan. It could also come from other agents, right? So if you think about something like planning for crowdsourcing, where you have many different agents, you have many different humans who are doing this crowd planning process for you. When they give you new information, your planner might need to update its plan that's currently executing. You might get new goals from either humans or from other agents, okay? And what happens then is, so think about the plan generation process, okay? Your planner basically generates a plan first, okay? The moment your planner publicizes that plan, okay, you're producing commitments in the world based on that particular plan. So think about, as a human, when you make plans to say fly out to AAA, right? And then you tell people about your plans to come to AAA, and obviously there are people that you know who might want to meet with you. So they say, okay, let's have lunch, on Sunday afternoon, or let's have dinner on Monday evening, and so on. So these are extraneous commitments that are being produced by other agents, for example, once you publicize your own plan, okay? And now what happens is, if you happen to change your plan, suppose you have to replan, okay? So suppose it turns out that you couldn't come to AAAI because there was a snowstorm, right? Now it's not just your plan that changes, but also the commitments that are induced because you publicize your plan to other agents. And in this work, continual planning while respecting commitments, I'm going to talk a little bit about how to essentially do that, okay? So to ground this in a human-in-the-loop planning problem, think about this following human-robot teaming scenario, right? So think about automated warehouses. So in fact, after we thought of this example, it turned out that Amazon actually is doing something that's very similar to this. So Amazon has these huge warehouses, right, which need to be managed. Now they can't do it in a fully automated fashion because they have to have at least one human, for oversight on these things. This is like Rao was saying, right? You need at least one human who is in charge of the decision processes, okay? But obviously you can't hire humans for everything, so you try to automate some of it. So Amazon does this, it's actually Kiva Systems that does this for Amazon, where they have these huge warehouses, and I'll show you an illustration soon. So the only human on the floor, almost usually always, is a packager, okay? So there's one guy who's standing in a corner of the warehouse, and this is the person who is issuing commands and goals and orders, and this is the person who is the last step of checking, right? So if you put together an Amazon box that is going to go out for delivery, this is the person who makes sure that everything is fine before it's actually sent off, okay? So that's the only human in the entire process, and that human issues goals to the robots, okay? And your robots are these little Kiva robots, these orange things. I don't know how many of you have seen visualizations of these Kiva robots. They're these little orange robots that can basically go from shelf to shelf in these huge warehouses, and they can transport items on shelves to the packager, who then puts them together and ships them out to you. And the goals are basically the order requests which come in dynamically. Okay, so it's not that you start with a set of goals and those are all the goals you have. Your goals keep changing, orders come in, orders get cancelled, a particular order has things added to it, things removed from it, and so on. Sometimes you go to a shelf and you find out that you're out of an item, right? Then you need to figure out what else to do about it and so on. So there are lots of things that can go wrong. So to give you an example, this is of course a very simplified layout of this whole Kiva robot planning thing, right? Which is that you have a warehouse layout, okay? And like I said, you have a human who is usually the only human in the entire process, right? So you have a human at the end of the warehouse to whom the packages are being delivered, okay? So that's your overall goal, that you need to deliver certain packages to the human. And then you have these orange things, which are the Kiva robots essentially, okay? And the robots can navigate this warehouse, which is basically, think of it as a grid basically, okay? And there are certain locations on this grid that give you access to shelves, and shelves have packages on them. So these robots, what they can essentially do is go to a particular shelf, get a package off of that shelf, and then bring it to you. And again, this is a simplification of the warehouse scenario, but that's essentially what you have. So you have agents which are basically your transports or your Kiva robots, right? And you might also have, for example, tow trucks if a robot breaks down in the middle, because these are huge places, these warehouses, right? And there's a lot of automation and things are going on and things might break down and so on. So what are some examples of things that might go wrong? We call them perturbations, right? Because if you need to replan, why would you need to replan? It's because things can go wrong in the world, okay? So what are some examples of things that can go wrong? So for example, your transports, your Kiva robots can break down, okay, in the middle of performing a particular task. So not only do they stop performing their task, they might also be blocking the way for other robots, for example, okay? So you need things like tow trucks and you need garages to fix them and so on, okay? You can also have packages that fall off of these robots, right? Because these Kiva robots are pretty simple robots. So you might, while they're moving, you might have packages that fall off, right? So then you need to go back and get another package to replace the package in that order and so on. And so there are many different things that could go wrong like that, okay? And the commitments that I'm talking about, so remember this notion of commitments, which I'll keep coming back to, was this idea that if you initially had a plan, in your warehouse, right, and something goes wrong, then what are the commitments that plan produced, okay? So examples of commitments in this scenario, and commitments are usually always between, they're from agent to agent, so that, a commitment is between two particular agents. In this case, your transport or your Kiva robot might have a commitment on holding a particular package. So it might have said, okay, I'm going to go and get that package, okay? And if it breaks down, that's going to affect that. You might have tow trucks that commit to towing transports that break down, okay? So suppose this guy broke down, then this tow truck might actually say, okay, I'll come pick you up and take you to the garage to fix you, okay? You can also have commitments on packages being delivered to the packager, okay? So a particular transport can promise to this packager that I will get this package for you, okay? So and if things go wrong, some of these commitments get affected, and the whole problem that we're going to be looking at here is replanning in the face of these commitments. So how do you honor some of these commitments when replanning is necessitated, okay? So there are many different theories of how to replan, and again, replanning has seen a lot of study in the automated planning community. One of these theories is to just abandon the previous plan, okay, completely. Just come up with a completely new plan, okay? So abandoning the previous plan is one way to replan. Another way to replan is to reuse as much of the previous plan as possible, okay? So the idea behind this is that obviously you expended some effort in coming up with the initial plan, okay? So maybe you want to reuse as much of that initial plan as possible in order to come up with the new plan, okay? So reuse parts of the original plan to produce a new plan. And then finally, the third notion, which I will be expanding on here in this particular presentation, is this notion of commitment from the previous plan, okay? So instead of being beholden to just some notion of form, like instead of being beholden and saying, the previous plan looked like this, okay? Or instead of throwing out the previous plan completely, you look at it in a more causal manner. So you say, what is it that the previous plan was achieving, or what was it promising? So those are the commitments that I'm talking about, okay? And what you have essentially is that if these commitments are between agents, so you have a multi-agent problem, okay, because these commitments are between agents, and you are reducing that inter-agent replanning problem, you're scoping it down to an intra-agent problem, okay? So if you're the agent that is doing the planning, okay, and something goes wrong in your world, and you have to replan, then you think of all the other agents that might possibly be affected by you changing your plan. Like, what are the commitments in the world that you are going to break by changing this plan, and can I actually retain some of those commitments? So that is commitment sensitive replanning, okay? That considers commitments from previous plans. So we're going to talk a little bit about that, and so I want you to remember those three ways of replanning in the context of examples such as these. And associated with those three different ways to replan, there are different replanning constraints, okay? So remember, I said the first way to replan is to just abandon your old plan. If you completely abandon your old plan, then it's unconstrained replanning. There are no constraints from the previous plan because you're completely abandoning it, okay? There is also similarity constrained replanning. So if this is the second type of replanning, right? That if you want to preserve or if you want to reuse some of the information from the previous plan, ways to do that are to, for example, do action similarity, right? So you say that I want my old plan and my new plan to be as similar as possible, or to minimize the number of actions in which the old plan and the new plan differ, okay? So this is the notion of action similarity. There's another notion of causal similarity, right? So if you think about plans, plans can be seen as sequences of actions, okay? A plan is a sequence of actions, or they can also be seen, these actions, they have causal links between them, okay? So action A is providing a particular precondition to action B, okay? Now that precondition is a causal link between action A and action B, okay? So instead of looking at just the names of actions, you can look at the causal links between actions, okay? And in any case, you can try to minimize the differences between the two plans. And then finally, the third way of replanning is this notion of commitment constraint replanning, okay? So you try to look at what are the dependencies between various agents' plans, or the actions that various agents are executing, okay? And then you project those commitments between these different agents into a new replanning problem, so that when the agent is replanning, it tries to preserve as many of these commitments as possible. So the agent is docked a penalty for violating a commitment, for every commitment that it violates, okay? Now, going with this theme of threes, right? So there are three ways to solve the replanning problem. There are three different constraints associated with them. And so obviously there are three solution techniques, okay? So one idea is basically to just use, classical planning, which is just, existing planning algorithms. You solve it, so you have an initial problem instance I and G. I is your initial state, G is your goal state, okay? And your problem changes from that to I prime, G prime, okay? So I prime is the new state of the world, something changed in the world obviously, okay? And then G prime is possibly a new set of goals, okay? So these are new goals that your agents are trying to achieve. And so you try to solve that new problem using a classical off-the-shelf plan, okay? So this is the way to replan where you completely abandon the old plan. You're not caring about what was in the old plan, alright? The second way is to use specialized replanning techniques. So this second solution technique for replanning, it corresponds to where you want to reuse as much information from the previous plan as possible, or you want to preserve as much similarity with the previous plan as possible. So you might do things like, for example, local search, right? You can do iterative plan repair. So you can say, here's the old plan, and this old plan obviously broke for some reason, okay? So can I start at the point that it broke, and can I try to iteratively repair that plan, keeping it as similar as possible to the old plan, okay? So there's some techniques like that. And then here I'm going to talk about this notion of compilation to partial satisfaction planning, which I'll explain in the coming slides. So the idea here is that the commitments, remember the commitments that we were talking about, what are the commitments that are generated, by the publication of a plan in the world? You try to model these commitments as constraints on the replanning process, okay? So you say that when I'm producing a new plan, when I'm replanning, okay, it's not just the planning problem anymore, but there's also these other extraneous constraints that are coming because I have to preserve the commitments that my previous plan was making, okay? So we'll talk a little bit about that. And before I move on, I just want to flash this picture of a generalized notion of replanning, okay? Since we're talking about replanning and decision support when humans are in the loop, okay? So here you will see that you have the planner, okay? And ostensibly the planner is supporting some agent. You can think of a robot here, you can think of some other smart program, whatever it is, okay? That the planner is supporting. And what happens is that your planner gets an initial state and a goal description. This is your problem statement basically, okay? The planner gets that as input and produces a plan, okay? Now obviously, there are many different things that can happen once the planner produces a plan, okay? The first thing, of course, is that the plan is sent off for execution, okay? But in some particular scenarios, before you're able to send the plan for execution, you might have to get it signed off by some humans, right? So remember the NASA scenarios that Rao was talking about, where you might still have an automated system that produces a plan for you, but you need a human to sign off on that plan. You need maybe a mission commander or a mission validator to sign off on that plan and say that, okay, this plan looks fine, right? So you might need to present it to a human for assessment, okay? At the same time, if you're dealing with a multi-agent scenario, right? If you're in some multi-agent application or in a multi-agent world, then you might want to publicize your plan to the other agents before sending it off to execution. So we're thinking about the cooperative scenarios over here, right? So you have multiple agents creating plans at once. You might want to send your plan out to other agents. So regardless of what you do, you eventually then end up sending your plan for execution into the world, okay? And then what happens is that something goes wrong in the world. There's a sensing event and you figure out that something broke in the world. So my old plan, this plan that I generated, is no longer valid, okay? What do I do now? So this is where all those different kinds of replanning come together, the 3 different types of replanning that I was talking about, okay? So what happens is when something goes wrong, you monitor, you have an execution monitoring system, ostensibly, that determines what's wrong with the world, okay? Why will your old plan not work anymore, okay? At the same time, you also have some constraints that are produced, okay? And these are the constraints that we were talking about. So for example, if you had shown your old plan to a human for them to sign off on, okay? Then there are some constraints saying that, okay, maybe you want to preserve similarity to the old plan. This is similar to what Rao was saying about if you do some annotations on a particular piece of paper or on something you're reading, and then you send it back and you completely change it again, right? Then there's a lot of effort that the human, in this particular case, will have to spend just on getting the context back for that, okay? So instead of doing that, you might want to preserve some notion of similarity to your old plan, okay? Similarly, when you have shown the plan to other agents, if you want to change it, there are some commitments on changing that plan, right? Because these other agents might have made some commitments on your plan. So you might want to take them into account as well. So that's sort of a generalized notion of replanning. And again, this slide just sort of summarizes the constraints that we were talking about, right? So these are all the different constraints that you have on replanning as a problem. And then corresponding to that were the 3 solution techniques that we talked about, okay? So if you have replanning as restart, which is you just abandon the previous plan, then you just use classical planning and solve the new instance, the new problem instance. If you have replanning as reuse, then you do local search approaches. So you basically start from the plan that failed, you start from the old plan, and then you try to minimize the differences with that plan while finding a new plan that will work in this new state of the world, okay? And finally, you have replanning to keep commitments. So what happens here is that you think of commitments as constraints on your plan generation process. So you think of them almost as additional goals, okay? So the planner has certain goals that it's trying to achieve, but then you also have some additional goals now, which are these commitments that you have to keep, okay? So think of these in terms of the example that I was giving you, right? With the warehouses and all of that, right? So some of your commitments might be, I need to get this package to the packager, okay? Now if this particular transport broke down, maybe you can put some other transport on the job, okay? And so on, things like that. So those are commitments. And I mean, some of this work is motivated by this realization that all plans are essentially made up of commitments, right? So you have causal commitments in plans. So if you think of a plan as a sequence of actions, right? The action that comes immediately before the next action, it's committing to give certain preconditions to that action. So that's a causal commitment, right? And you might also have multi-agent plans where agents, if they're all acting in the same world, they either enable or disable conditions for the other agent. So there are commitments between agents with respect to that as well. And commitments can be thought of as goals, right? So you can add them as additional constraints on the planning process, okay? And that's essentially what we wind up doing here. Now, one advantage of reasoning about the replanning process in terms of commitments is that you can basically define it in terms of metrics, okay? So now you can start thinking about, here are various candidates for the replan, okay? So my old plan broke, and here are many different plan candidates that I can come up with when I'm replanning. How do I rank these candidates, okay? Is there a metric that will allow me to rank these various candidates? And so it's useful to think of commitments in that particular case, because you can think of these replans as breaking commitments, okay? And you want to maybe take the plan that breaks the least number of these commitments, or it minimizes some notion of commitment sensitivity, okay? And obviously, in order to come up with that metric, you need a notion of what it means to break a commitment, okay? So if you break a commitment, are you assessed some penalty, okay? Similarly, if you keep a particular commitment, do you get some reward instead, okay? So if you preserve some commitment with the old plan, do you get some reward, okay? So you might get a reward R for fulfilling a commitment and a penalty P for violating it, right? And this, you can think of this in terms of if you have multiple agents, and the agent that you're planning for, it basically engenders a bunch of commitments because it publicized its plan. Then when it tries to make a new plan, are there values, are there reward and penalty values on breaking these commitments or on keeping these commitments, okay? Now, one non-trivial question obviously is, how do you set values for these rewards and penalties? So for agent-based commitments, you can actually try to get these values from real-world applications, right? So for example, NASA has estimates on how valuable certain windows are, right? So you have observation windows, okay? And you have estimates on how if you lose this window, how much time is it going to be before you get another window to observe the same kind of phenomenon and so on, okay? So you can actually set values on how, on what penalties or rewards you get on satisfying these commitments. And then for similarity-based approaches, where you're trying to maximize the similarity with the previous plan when you're replanning, right? You can say that for every different action that I have from the previous plan, I'm going to assess you a penalty, okay? So if my old plan and new plan differ, say, in 4 places, then I'm going to have 4 times that penalty unit, okay? So you can put it in terms of that. And one of our contributions in this work was basically to come up with a way of compiling some of these replanning techniques to something known as partial satisfaction planning, okay? So partial satisfaction planning is essentially, it's a technique where basically you think of, so you have planning goals, okay? Your goals are no longer hard goals, you think of them as soft goals, okay? So your plan need not necessarily achieve all of the goals that are part of the planning process, okay? If you achieve a goal, you get a reward R, and if you don't achieve it, you get a penalty P, okay? So it's almost like you're relaxing the notion of goal, okay? So that's partial satisfaction planning, and we basically had a technique to compile action similarity and causal link similarity. So various ways of replanning, how do you compile them into, into a partial satisfaction planning problem? I'm not going to go through all of this, but there is work that exists on this. So this is essentially the idea where you can think of the replanning problem as planning subject to a certain set of constraints. Okay, in this case, the constraints that I was talking about were either similarity constraints or they are commitment constraints, right, to other agents, to the plan that you publicized. Okay, and so those are the constraints that we were talking about. But you can also have a notion of interaction constraints. So this is that work that Rao was mentioning in the introduction on grandpa hates robots, right? So you can think easily, right? So instead of thinking about a multi-agent scenario like the Amazon warehouse, right? Think about a human-robot interaction scenario where instead of teaming together, your robot is trying to actively avoid humans, okay? Because it knows that humans don't necessarily like being around you, okay? So in such scenarios, what you can do is you can define certain conditions, okay? Certain constraints, certain interaction constraints that basically constrain the plans that the robot is able to come up with, okay? So you say things like, don't enter the bathroom while it's occupied, okay? Or don't vacuum in a particular room while I'm reading, okay? So these are now constraints that eliminate some of the possible plans that your planner could come up with for the robot, okay? And so, there are many different examples of this, and I'm not going to go into details of what this does, but there is now work on considering these explicit constraints. Once you name these constraints, okay, how does your planning process change in order to take these constraints into account? So this part was basically about explicit named constraints, okay? So think about interaction constraints in this grandpa hates robots work, or you think about commitment constraints when you're replanning in the continual planning work, okay? But there's also a way of taking implicit preferences and constraints into account, and Rao's going to talk about that part now, where he talks about taking a notion of implicit constraints. So if you're not told that this is a particular constraint that needs to be respected while planning, but you can figure it out based on showing plans to humans, for example. How do you deal with that? So, Rao, you want
So with any luck, this would be the last, one more change, and that's it, and then we'll be fine, hopefully. So anyway, as Karthik said, I'm going to talk a little about how to handle the incomplete models, and the models can be about constraints, the preferences of the human, as well as the dynamics. As a kind of a recap of what we have been doing until now, you notice that we have mostly used until now the existing planning techniques and sort of to the challenges of human-in-the-loop planning. So for example, he looked at how to use plan recognition techniques for doing the interpretation, and then he also looked at how to use the partial satisfaction planning and replanning to support continual planning, and what are the ways in which they have to change. This other part that I'm just about to talk about is basically what happens when you have incomplete models, and normally the traditional planning techniques don't actually look at incomplete preferences and dynamics. So in some sense, this is stuff that we've been doing that, it is connected to planning techniques, but it's also sort of a different problem solution concept. So that will take a little bit of getting used to. So basically, as the traditional line in classical planning has been, start the classical planning and keep making the problem more expressive. So introduce stochastic dynamics, introduce temporal dynamics, introduce metric quantities and so on. And what we are looking at right now in this part of the talk, as I have already motivated in earlier on, is basically you want to consider what happens to planning problem when the preference information and the dynamic information is incomplete. Okay, so that's what we're going to look at, and so we've been looking at this as a model-light planning. That means the models are incomplete, and then so it has uses in places outside of human-in-the-loop planning, but it also has significant use within the human-in-the-loop planning, because as I mentioned, in many cases there will be incomplete models in the human-in-the-loop planning. Okay, and this was something that I was mentioning that. That the planner in the context of human-in-the-loop planning will likely have an incomplete model is something that people have recognized even in the beginning times, even in the 90s when they were looking at mixed initiative planning. So this was actually a sort of an excerpt from Allen's paper on trains, where he basically says, look, we don't believe that planners will have complete models in, when you are humans and planners in the same loop. And so we are actually going to, even though the problem that we are looking at happens to be a map following for which you can get complete model, we will experiment with a planner which deliberately has lesser model, incomplete model. Okay, so that's sort of, it's not something that we suddenly recognize, it's just that not too much work was done at all in incomplete models. So that's what we're going to look at a little bit quickly today for this part. Okay, now whenever you have incompleteness, the first thing is, why don't we just learn? Why don't we wait until the model becomes complete? Then we can do the usual traditional planning. That's a reasonable temptation. But then that is kind of not a good answer, because you will always have incomplete models. At any given point of time, you will always have incomplete model of preferences and dynamics. Over a period of time, you might be able to improve your knowledge. So you should do learning, but you should also know what to do with the incomplete model that you currently have. Okay, so this part mostly is about what to do with the incomplete model you have, and I'm not saying you shouldn't learn, and there is actually a lot of work that we have done and other people have done on how to learn to improve models. We'll mention a little of it here, but my focus is on what matters, what does it mean to do planning with incomplete models. Okay, so here are some challenges for just handling incomplete models. One, of course, you need to sort of think of how do you circumscribe the incompleteness in the model. So for example, if I just give you a model and say it's incomplete, I have no idea why it's incomplete, then what can you do? You just use the plan model to come up with a plan, and you say it might work, it might not work, I have no idea. Okay, so the question, of course, is if you can circumscribe the level of incompleteness in the model, sometimes you might be able to make more interesting guarantees. The other thing is, if there is incompleteness in the model, you will actually, the question of what is the solution for a planning problem changes. We'll notice that, for example, for incomplete preferences, we will start talking about a diverse set of options of plans. So you don't generate one plan, you generate multiple plans and present it to the user. And for incomplete dynamics,